Imagine crossing 800 kilometers of sand without finding a single drop of water. Sun directly overhead. Dunes shifting like waves frozen in time. A silence broken only by wind scraping across stone. This is the Sahara we know, the largest hot desert on the planet. A place that seems to have been hostile to life since the beginning of time. But dig beneath that sand, or simply look closely at the exposed rock, and that certainty starts to fall apart. There are layers of sediment that only form at the bottom of lakes. There are the fossilized bones and scales of freshwater fish, preserved hundreds of kilometers from any river, and carved into the stone by human hands thousands of years ago. There are images of hippopotamuses floating, crocodiles lurking, herds of elephants and giraffes crossing what is today an ocean of dunes with almost no life left in it. None of this is legend, it is record, and the record tells a story that seems almost impossible to believe. For thousands of years, the heart of the Sahara was green. Not a continuous jungle, not a uniform tropical paradise, but a living mosaic of savannas, rivers, lakes, and people on the move, where today only a sea of silicon remains. The question we're going to chase through this entire journey is simple to ask and enormous in its implications. What had the power to transform the largest desert in the world into a territory of water, life, and human culture? And what had the power to undo all of it again? Before we go on, one invitation. If stories like this, written into the rocks and sediments of our own planet, have the power to change the way you see the world, subscribe to channel. This kind of reconstruction, rebuilt fossil by fossil, grain by grain, is exactly what sustains every video we make here. And you'll want to be around when the next piece of this puzzle turns up. The answer begins far from the sand, far even from Earth itself. It begins in space, in an almost imperceptible wobble of the planet. Earth doesn't orbit the sun in a perfectly stable way. Its axis slowly wobbles like a spinning top losing speed, in a cycle that completes roughly every 21,000 years. That wobble has a technical name, orbital precession, but its effect is simple enough to picture. Over thousands of years, it changes which time of year each hemisphere receives the most direct sunlight. About 11,500 years ago, according to much of the record. Other climate markers push that date back to nearly 15,000 years. That oscillation placed the northern hemisphere in a position that intensified summer heat over the African continent. More heat over land means more hot air rising. Rising hot air creates low pressure, and low pressure pulls inward something that is normally confined to the equatorial belt, the West African monsoon, the engine of rainfall that today barely grazes the southern edges of the Sahara. An almost invisible tilt in a planet's axis, sustained for thousands of years, was enough to push tropical rains hundreds of kilometers into what is today the most unforgiving desert on Earth. But astronomy alone doesn't explain the scale of what happened next. Climate models that try to recreate the orbital effect on its own produce a wetter Sahara, yes, but not wet enough to sustain lakes, rivers, and savannas at the intensity the sediments reveal. Something was missing, and that something didn't come from space. It came from the ground itself. As soon as the first extra rains began to fall, plants started sprouting where there had only been bare rock and sand before. Dark vegetation absorbs far more sunlight than pale sand does, what scientists call a change in albedo, and that extra heat trapped near the surface helps intensify the air currents that carry in even more rain. At the same time, soil covered by roots and leaves releases much less dust into the atmosphere than exposed soil does. Less dust means clearer skies, which changes how solar energy is distributed and reinforces the rainfall pattern all over again. Water pooling in lakes and marshes evaporates and moistens the air over the continent, feeding the cycle once more. In other words, the Earth built its own rain-making machine. A small orbital tilt lit the engine, but it was vegetation, soil, and water that kept it running for thousands of years in a feedback spiral that no single factor could have sustained on its own. That's why researchers describe this period, the so-called African humid period, not as a simple shift in rainfall, but as a complete reconfiguration of North Africa's climate system. And what that machine produced over millennia sounds almost like science fiction today. Where satellites now register only dunes, scientists have identified entire ancient riverbeds, scars of water that once cut clean across the desert from end to end. Basins now known as paleo-lakes, fossil lakes, reached at certain points dimensions researchers compare to true inland seas. Analysis of pollen preserved in sediment allows scientists to reconstruct, plant by plant, how far vegetation advanced. Tropical forest formations reached latitudes close to 20 degrees north of the equator, a band that is entirely arid today. Farther north still, savannas and woodlands of the kind that today only survive along the Sahara's southern edge in the region known as the Sahel, stretch to at least 28 degrees latitude. Kilometer after kilometer of territory that today belongs entirely to the desert. That means ecological zones separated today by thousands of kilometers of sand were, at that time, practically neighbors. A traveler back then could have walked from a savanna teeming with antelope to the shores of a lake churning with fish without ever losing sight of water or shade. And this wasn't a timid desert with scattered puddles. It was a networked water system. Seasonal rivers connected entire basins, letting animals and, eventually, people move through continuous corridors from one side of the continent to the other. One of these systems, the basin that today sustains what remains of Lake Chad, reached, in its most expanded phases, an area comparable to entire countries, reduced today to a fraction of what it once was, but still functioning as a physical reminder of just how much water this territory once hosted. And where water is abundant, wildlife responds. The rock walls of Tassili Niger in Algeria and the Tedrar Takakus Massif in Libya hold thousands of rock paintings and engravings documenting that world in striking detail. Hippopotamuses submerged up to the neck, crocodiles gliding along muddy banks, herds of elephants, long-necked giraffes, oroches, the wild ancestors of modern cattle, and antelope in hunting scenes. These images aren't loose artistic fantasies scattered through time. They match, point for point, the fossils found in the same geological strata, the pollen from the same sediment layers, the landscapes that climate reconstruction projects for that period. The art confirms the science, and the science confirms the art. It's worth understanding, briefly, how researchers managed to see a world that vanished millennia ago without traveling through time. Orbital radar, the same technology used to map the surface of other planets, can penetrate a few meters of dry sand and reveal beneath today's dunes the ghostly outline of ancient riverbeds, scars that water carved into rock long before any dune ever existed, sediment cores pulled from the bottom of lakes that still survive or basins that are today completely dry. work like a stacked archive, layer upon layer, each one corresponding to a stretch of time, each one holding grains of pollen, shell fragments, and chemical traces of the water that once sat there. Radiocarbon dating, applied to bone and charcoal, and luminescence dating, applied to grains of sediment, turn these layers into concrete dates, with known and stated margins of error. It's the combination of these tools, satellite, sediment, chemistry, and dating, that turns an ordinary dune into a legible page of the planet's history. But if every engraving tells a scene from a thriving world, the next question is unavoidable. Who were the people who stood there to see it? And how did they live inside that temporary abundance? The most complete answer we have so far comes from a single place, a rock shelter in southwestern Libya called Takar Kori, tucked inside the Tadrart Akakus Massif. There, layer after layer of archaeological sediment records a nearly unbroken sequence of human occupation beginning around 10,200 years ago. The first inhabitants documented at Takar Kori weren't herders, they were hunter-gatherer fishers, people living off the hunting of wild animals, the gathering of plants, and, notably, fishing in lakes and rivers that today simply don't exist in that region anymore. Fish bones and freshwater mollusk shells, found hundreds of kilometers from any body of water today, prove that these communities depended on permanent aquatic resources, not on occasional rain puddles, but on hydrological systems stable enough to sustain generations. It was a world of mobility, groups moving between lakes, following the seasons, following herds, following the very logic of a territory that was generous but never uniformly easy. Then something changed. Around 8,300 years ago, Takar Kori's archaeological sequence begins to register a new economy layering itself over the old one. The first signs of herding. The bones of domestic cattle start appearing alongside the bones of wild game. This doesn't mean hunting and fishing vanished overnight. The evidence points to a gradual transition, almost a coexistence, between a way of life built entirely on the wild and another that was beginning to domesticate part of it. And it's exactly at this turning point that the rock art changes subject. Scenes of solitary hunting give way to scenes of herding, with human figures driving cattle, marking territory, organizing life around livestock. One detail is worth pausing on. The cattle appearing in these scenes descend ultimately from the wild aurochs, a massive animal, extinct today, that still roamed free across the Saharan savannas of that era. Domesticating this animal, or absorbing already domesticated lineages arriving from other regions, meant trading part of the unpredictability of hunting for a more direct, if labor-intensive, control over one's own food supply. But why would a community abandon, even partially, a system that had already worked for generations? The most likely answer hides inside a single word, carrying the full weight of this documentary: instability. Around 8,200 years ago, the archaeological record across much of North Africa shows a sharp drop in the density of human occupation, an intense, dry event known today among climatologists as the 8.2 thousand-year event that temporarily interrupted the bounty of the African humid period. It wasn't the definitive end of the rains, but it was a warning. The system that had seemed eternal had cracks in it. Communities depending solely on the unstable abundance of wild lakes and savannas needed a more resilient strategy. And herding offered exactly that. A herd can be moved, can follow a family in search of pasture, can serve as a mobile food reserve in a landscape already showing signs that water wouldn't always stay in the same place. The natural question any archaeologist would ask, faced with this, is, did these domesticated animals provide only meat, or was something more sophisticated happening? The answer arrived in an unlikely form: fat. Ancient fat, invisible to the naked eye, trapped inside the microscopic pores of pottery shards broken thousands of years ago. Using chemical analysis techniques capable of identifying lipid residues absorbed into the clay during cooking, researchers proved that Takarkori pottery vessels, dated to the 5th millennium BC, contained the characteristic molecular signature of milk fat, not roasted meat fat, not generic animal grease, processed milk, likely boiled, strained, or fermented. This is the first unambiguous chemical evidence of dairying anywhere in the Sahara, and it completely reshapes the picture we have of these herders. We're not talking about people who simply slaughtered cattle whenever they needed food. We're talking about communities that had discovered one of the most ingenious survival strategies in human history: extracting continuous nourishment from a living animal without needing to kill it. A milk-producing herd means food available every single day, not just on slaughter day. It means food security in an environment that was slowly, quietly becoming less generous. And it also means mobility. People who could travel carrying their own food source with them, without depending entirely on the local abundance of one lake or one specific savanna. In a landscape swinging between plenty and scarcity, milk was, quite literally, liquid life insurance. Before we move toward how this story ends, take a moment to consider what's being said here. People living 7,000 years ago, in the heart of what would become the largest desert on the planet, had already developed a dairy-based economy. If stories like this, evidence hidden inside a broken pot, capable of rewriting our sense of what ancient peoples were able to accomplish, spark your curiosity, drop a like on this video. That reaction is exactly what helps other people find these stories too, and it's the fuel that keeps Channel digging, quite literally, deeper and deeper into the past. But not even the most sophisticated ingenuity is an indefinite match for a planetary shift. If Earth's orbit turned on the monsoon tap over the Sahara, that same orbit, millennia later, began turning it off. And here, the story takes on a complexity that any honest scientific reconstruction has to respect. The end of the African humid period didn't happen the same way, at the same pace, everywhere at once. Sediment cores pulled from the ocean floor off West Africa's coast register spikes in Saharan dust, a direct sign of exposed, dry soil, suggesting a relatively fast transition around 5,500 years ago, unfolding, according to some of these records, over just a few centuries. That's the origin of the somewhat oversimplified idea that the Sahara dried up overnight. But other archives tell a different story. Lake Yoa, a small permanent lake that survives to this day in the Unianga Kabir region of Chad, preserved sediments recording a far slower ecological succession stretched between roughly 5,000 and 3,000 years ago. A gradual withdrawal of vegetation and moisture, not a sudden collapse. The two versions don't contradict each other. They describe different regions, sensitive to different local factors within the same continental process. Saying the Sahara dried up in 200 years may be true for one specific marine core and misleading as a description of an entire continent. The retreat of water was, in the precise term scientists use, time transgressive. It began earlier in some regions, persisted longer in others, advancing like a slow, uneven tide, not like a switch flipped off all at once. It's worth pausing here for something important, because it's tempting and simplistic to blame the herders themselves for this outcome, as if grazing had exhausted the soil and accelerated desertification. A quantitative study that cross-referenced archaeological population data with climate simulations arrived at a conclusion that pushes back against that instinct. There is no evidence that human presence and herding hastened the end of the African humid period. If anything, the vegetation cover sustained locally by herding may have delayed the advance of aridity in some areas. The dominant force behind the end of this era remained climatic. The same orbital precession that once intensified summer insolation over the northern hemisphere, having completed its slow cycle, began weakening it instead, progressively undermining the monsoon that had once carried life into the desert's interior. The very machine that vegetation and lakes had helped build also worked in reverse to accelerate the collapse. Less rain meant fewer plants. Fewer plants meant more dust, and more sunlight bounced back into space, and that new atmospheric pattern reinforced the drying trend all over again. The same feedback mechanism that once sustained the green Sahara became, centuries later, the engine of its desertification. And what archaeology records, when checked against this climate data, lines up with striking precision. Hunter-fisher occupations expand rapidly around 10,500 years ago during the first wave of African humid period abundance. They retreat during the dry event of 8,200 years ago. They grow again, this time driven by the new pastoral economy in the period that follows, and they contract once more around 5,500 years ago, exactly when the marine dust records point to the sharpest turn toward aridity. This pattern of expansion, retreat, and reorganization isn't the portrait of a passive population simply waiting to vanish as the climate worsened. It's the portrait of human communities actively responding through mobility, through changing economic strategy, through collective decisions about where it still made sense to keep living. So the question left standing isn't, why did these people disappear? Because they didn't. The right question is, where did they go? And what did they carry with them when the lakes, one by one, began to dry up? The most recent and most surprising answer came once again from Takarkori. This time not from pottery or rock art, but from genetic material itself, preserved in human bones nearly 7,000 years old. For decades, a common hypothesis suggested that as the Sahara dried, waves of migrants arriving from other parts of Africa, or even from outside the continent, had completely replaced local populations, bringing herding with them fully formed. Full genetic analysis of these Takarkori individuals told a subtler story. It revealed a deeply rooted North African lineage, distinct from sub-Saharan African populations and also from Near Eastern populations of that period. An ancestry that appears to have remained relatively isolated and stable in North Africa for a long time, even through the shift toward herding. That suggests something remarkable. Herding didn't necessarily arrive through the wholesale replacement of one people by another. It spread, in large part, through cultural transmission, techniques, domesticated animals, and knowledge passing from group to group, adopted and adapted by the local populations already living there, without requiring the genetic erasure of people who had called that land home for generations. Ideas, herds, and practices crossed the Sahara more easily than entire peoples ever needed to be replaced. That doesn't mean nobody moved, though. As water retreated unevenly across the continent, the communities depending on it were forced to concentrate wherever resources still remained, in ecological refuges, pockets of moisture that resisted the broader aridity for longer, and toward frontiers we recognize well today, the Sahel to the south, where savanna still survives today in a reduced form, the Maghreb to the north, closer to the Mediterranean, and perhaps the most significant destination of all, the Nile Valley, to the east. The Nile had something most of the shrinking Sahara no longer had, a permanent flow of water, fed by rains falling in distant regions in Ethiopia and East Africa, largely immune to the drying settling over the continent's interior. As inland lakes disappeared one after another, it's reasonable, and this is a widely discussed inference, not an absolute certainty, that part of these displaced populations gravitated progressively toward that reliable water corridor. Here, though, scientific honesty demands caution. It would be simplistic and inaccurate to claim that the Sahara's desiccation single-handedly created Egyptian civilization. What the data actually supports is far more nuanced, a striking temporal coincidence, and a plausible migratory pressure within a social and environmental process that had multiple causes, multiple phases, and multiple protagonists unfolding over centuries. The story of pharaonic Egypt wasn't born from a single climate event. It was born from a complex convergence of factors, of which the Sahara's contraction was, at most, one piece. What is clear in any case is this: the Sahara didn't die when the rains retreated. It spread out, it transformed. Its waters, its herds, its techniques, and in part, its own people went on existing, just reorganized across new geographies, adapted to a drier world, carrying with them memories we can now only read through fish bones buried beneath dunes, milk fat trapped in broken pottery, and hippopotamus figures carved into rocks that nobody today associates with lakes. There is something deeply unsettling, and at the same time, deeply human about this story. The Sahara we know, vast, hostile, seemingly eternal, is just the portrait of a single instant within a much larger cycle. A cycle that has already repeated itself several times across hundreds of thousands of years of the planet's history, always at the same slow pace set by the tilt of the Earth relative to the Sun. What we today call a definitive desert may be, on a geological timescale, just a pause, a phase between a green that already existed and another green that, in theory, could return thousands of years from now when the same orbital oscillation completes another turn of its slow, patient cycle. That should change how we look at any landscape we assume is permanent. The dunes that today seem to define North Africa forever were, more than once, the bottom of a lake teeming with fish. The borders that today separate savanna from desert, culture from culture, have already shifted hundreds of kilometers in both directions, pushed not by wars or empires, but by the silent geometry of a planet spinning around a star. And perhaps the deepest lesson this reconstruction leaves us with isn't about climate at all, but about people. Faced with a world that opened up and then closed again, these communities didn't vanish and didn't freeze in place. They hunted when there was game, fished when there was water, domesticated when domestication made sense, and moved when moving was the only sensible choice. They traded certainty for more flexible strategies. They turned milk fat into food security, turned knowledge into something that could travel farther and faster than any entire people would ever need to travel. If there's a thread connecting those people to us, maybe it's exactly this: the ability to rebuild life, even in a different form, when the world around insists on changing the rules. The next time you see a photograph of endless dunes, the kind that seem to represent the absolute opposite of life. It might be worth remembering that beneath that sand lies the sedimented proof of a green world, of lakes once teeming with fish, of herds and entire families who built a thriving life there, and that the landscape we consider definitive is, in truth, just another chapter within a far longer breath than any single human story could ever hope to contain. If this reconstruction, built from pollen, bone, dust from the ocean floor, and fat hidden inside broken pottery shards, has changed even a little the way you see a desert, consider subscribing to channel and turning on notifications. There are still countless other landscapes that seem eternal today, but that science has already proven were something entirely different in a past not so distant after all. And the next one of these stories might be right beneath our feet.